Okay, thank you very much for coming, and it is meeting number 15, lecture number 15 in computational chemistry. So we were accumulating some theoretical knowledge about how computational programs are working, and in addition, all of you were putting enormous effort into getting the practical skills that are not formal part of the course. But I want to stress and appreciate that all of you were sacrificing your time, coming after hours into computer lab and doing some practical things. So today we are going to share between us who each of members of the group was getting some new skills, and it is a time to share them. So the exercises, the skills that we were trying are designed to accompany the lecture material. And there are several topics that will help us to apply everything that we were discussing in class to our everyday research life. So please please come one after another in a sequence. Please come to the stage, take the microphone, you can mount it on the ear or just hold it in the hands, and then select your own presentation to bring it on the screen. And let's agree on let's say 4 minutes for presenting and 2 minutes for questions. And I foresee that it will be very hard. Some of us will take more, but we will try to make it not very long. So the last time when we met and made a practical presentations, the oral presentation session, we were sharing the experience of very introductory step in bringing up the software and building the models. Today we are going further. We are discussing how to process with electronic structure calculations and which practical steps can be made and should be made, with a little background knowledge for which is necessary to understand those steps. So here is the schedule, an overview of available electronic structure methods, the important step of selection basis sets, then preparing the data for computation, analyzing data for computation, and building molecular orbitals and analyzing the energies of molecular orbitals. Okay, I want also to announce that all slides that you have prepared were composed in a single document, and I've distributed so that you can look on it while presenting. Please feel free to raise hands to question the speaker, because it is the way how we help each other to learn maybe something new. And the copy of all the slides combined as a single PDF is also placed on the D2L. There are two additional sets of handouts. They are a couple of pages from the textbook. One of the pages, one of the handouts is illustrating the selection of resources and compares advantages and disadvantages of different methods, and it presents on the last page a chart that shows time spent for computation as function of selected method and selected basis. And another handout shows a little example of how people were computing molecular orbitals 20 years ago. And at the last page of this handout, there is a little paragraph, which is page 113, providing a disclaimer how nice and important they are and how untrustable they are. So they are only mathematical abstractions then that sometimes help to understand physical and chemical processes. So I would like to finish the introduction and give the stage to the first speaker, who's Jensen.
Okay, so I'm going to talk about electronic structure methods that are available in the Gaussian software. Basically, the goal of our electronic structure calculation is to get the structure, the geometry optimization, absolute and relative energies. We can calculate charge distributions, dipoles, vibrational frequencies, and a lot of other things just based on your needs. And we use this to either back up experimental results that experimentalists have found, or possibly predict some unseen phenomena. So like, if something's happening in a reaction and they're not sure what, they can run a calculation to see if we can find out what the intermolecular interactions are doing that's making this happen. So these are a few of the methods available in Gaussian. We have molecular mechanics, which we all worked with in the first lab. Semi-empirical, Hartree-Fock, DFT is density functional theory. MP2 is a perturbation theory. CCSD is coupled clusters with single excitations and double excitations. BD, Brownian dynamics, and CASSCF is complete active space self-consistent field. So we're going to go through some of the most popular, and that would be the ones on the left in bold. So molecular mechanics just uses force fields. It's not very accurate, but if you just need a quick geometry optimization, you might be able to use it. Semi-empirical is based on Hartree-Fock, but it uses a lot of approximations. And one of those is parameters that they get from experimental data. And so this falls short when the experimental data is not available, or it doesn't match up to your model or the molecule you're studying. And the two electron integrals are approximated or negated, so it basically assumes there's no electron interaction, which obviously is a big downfall in a lot of molecules. Hartree-Fock is what we're studying right now. It's also known as the self-consistent field, and it uses the n-body wave function approximated by single Slater determinant. So I think we just covered that in class. DFT, I would say, is probably the most popular. Properties of many electron system is determined, and it's mainly used for ground states. I think you can get pretty accurate results with one excited state, but you can't do doubly excited. MP2 improves on the Hartree-Fock method by adding electron correlation effects. And so with precision, MP2 is best. It used to be that Hartree-Fock was more precise than DFT, but recently with hybrid functionals, we are able to get a little more precision off that. And then semi-empirical and molecular mechanics, and you can see this is an inverse relationship with computational costs. When you use the more precise methods, you can only use very, very small molecules or just a few atoms in order to get it in time. Otherwise, it could take years to calculate. So how to choose different methods. Log into HPC and navigate to the directory. Get gausview up. Open your model, your .com model, or .log model, right? Select calculate, click on methods, and then select from the manual. So we click calculate, we click the methods, and then we have a list of our possible different methods we can use. You can also do this from the command line. So we have our .com file, and if you type VI or nano, you can see this come up. And right here in this fourth line is where you can change your method. So HF would be Hartree-Fock, and then the basis is this one right here. And I think if you go to Gaussian.com, it'll tell you which methods you can use and then how to, I guess, summarize them to use in your. So basically for basis function, multiplicity, and spin, Jon and Vinu will cover this, or ask Dr. Keeling, because I'm not sure. That's it.
Okay, let's thank the speaker. So any questions? Anything, objections, or a wish to learn more? Mohammad, please turn on the mic so that. Okay, then tell whatever you like, and we will.
Hmm. Yeah. It depends on how large your molecule is. So if you have a really small molecule, you might as well use the more precise calculations because it won't take as long depending on how much time you have. But I think in general, you want to be as precise as you can within the time limit you have. So I know DFT probably takes like a day for, I think we had a 120 atom system, so depending on how much time you have. Well, they'll be different, and the more precise will give you more accurate results. So depends. Like for drug studies, when you are studying a molecule running in the bloodstream, you want to be as accurate as possible because you can't really mess with those when they link up. So they generally just do geometry optimization for that, and that you can use more precise methods.
No more questions? Okay, let's thanks, Stephanie. And the next speaker is Vino. Please come. In order to swap between different presentations, they are arranged here on the screen. So you just click and bring it up. And click here for launch the presentation.
Good afternoon, everyone. Can you hear me, SDSU?
Yes, we can hear you.
I would like to introduce an nomenclature of some basis sets. What is the important theme of the computational chemistry is the calculation of the molecular orbitals. Using these molecular orbitals, we can do various calculations like calculating the energy of a system, electron density, electrostatic potential, transition state, and frequency. But calculating molecular orbitals is not that easy, but the computer does that for us. In order to calculate the molecular orbitals, we need to provide some basic information that is called as the input files. So what are these examples of these input files? Here you can see kind of a basic picture what the chemist decides and what is the computer calculates for us. We can give starting with the geometry of the molecule, we can give in the form of bond lengths, bond angles, or dihedrals, and the type of the calculations can be of single point energy, frequency, transition state, electron density, or electrostatic potentials. And then like starting with the set of the mathematics and approximations, like different models, what Stephanie gave some introduction about the molecular mechanics, semi-empirical or Abiancio, or type of approximations such as Hartree-Fock or molar placet, etc. And thus, with using these as a form of wave functions, computer calculates the atomic orbitals from using that atomic orbitals, using the linear combination of atomic orbitals, it gives us the molecular orbitals. So in general, the definition of basis set is a set of functions which are combined in linear combinations to create the molecular orbitals. There are two types of basic functions. One is atomic Slater type orbitals, that is STO, and Gaussian type orbitals, that is GTO. Both these calculations works fine for smaller molecules, But if the atoms exceeds 30 or more, then there occurs a major discrepancy between these two models. The STO, that is the Slater type orbitals, are more accurate, but it takes more time, whereas the Gaussian type orbitals are faster compared to these STOs, but they are less accurate. So in order to get any one of these, we have to compromise either with the time or the accuracy. To overcome this difference in the STO and GTO, what scientists did is they added several GTOs in order to mimic the STO's accuracy. Thus, we can model the STO equation, and the new form of the equation is called as STO hyphen kg, where k is an k or n, you can use it. That k or n is an integer that represents how many number of GTOs were used in that particular calculation. Here is an example. You can see STO3G, where the 3 is number of GTOs used in that, and STO6G is 6 is the number of GTOs used in it. There are few modifications or something included in these basic sets, which are plus or asterisk. The most common addition to this basis set is probably polarization function, which is denoted by an asterisk. If you can see just an example, STO3G star means it's a polarized version of STO3G. If we add two asterisks, that means that the polarization function is added to the light atoms such as hydrogen and helium. Another common addition is the plus sign, which is called as the diffuse function in the Jon Vogel method, or else using the Dunning type, it is called as AUG, that is augmented. If we use two plus signs in the basis set, that means same as the asterisk, that means the diffuse function is added to the lighter atoms. So in minimal basic functions, only enough functions are employed to contain all the electrons of the neutral atom. If say like for example, the 0th row in the periodic table such as hydrogen or helium are denoted with single S function, or the first row elements are denoted by 2S function and 1 P function, and the second row are 3S function, 2 sets of P functions. If you say that as a double zeta, it means that the basic functions were doubled. If you see the 0th order, it has single S function in the normal basis set, but if it's denoted as double zeta, that means it has 2 S function, same as the way you double the S functions in the first row and the second row. There are triple and quadruple zeta were also available. That means that the basis functions were tripled or 4 times of the normal basic function. So how to denote these basis sets? Jon Vogel notation gives us the x, y, z, g, which means in the x is the number of primitive Gaussians comprising each core atomic orbital basic functions, and the y and z indicate the valence orbitals, which are composed of two basis functions. One is the linear combination of y primitive Gaussian function, and the other is composed of the linear combination of z number of primitive Gaussian functions. And also in this case, the presence of two numbers after there sometimes you can see like 6, 3, 1, 1, or those kind of two numbers means that the basis set is a split valence double zeta basis set. And split valence triple and quadruple means it will have like 3 numbers before the G or 4 numbers before the G. So here is an example which shows like 6311 plus G star. It means it is a triple split valence basis set, and the inner part of the valence orbital is represented by 3 GTO, and the middle part of the valence orbital is represented by 1 GTO, and the outer part of the valence orbital is represented by 1 GTO. And the plus sign in the basis set indicates that it has one set of diffuse function on atoms heavier than hydrogen and helium, and this asterisk indicates that it's the polarized version. How to apply or how to include this change the basis set in our Gauss view. Draw your model in the Gauss view and go to calculate Gaussian calculation setup. In there you can see there is a basis set which you can have a long list of different basis sets available, and also, as I said, the polarization and diffusion can also be included. In that you can there is a small list down window. You can see the plus signs and also the asterisk signs. In this way you can include the basis difference in the basis sets in your own model. Thank you.
Oh, but thank you, speaker. You did a lot of work preparing it. Thank you. So, any questions from the audience? I have one. So, are there any restrictions for the atoms? Like, if you are using transition metals, would this work, or it is supposed to be one needs to do something completely different?
I think you can go for LAN, L2DZ, those kind of basis sets when we are using some heavier atoms, because the 631G and the 6311G, these are okay for a smaller like carbon hydrogen atoms like models. But if you are having transition metals or lanthanide type of metals, you need to go for some rigorous basis sets.
Okay, okay, very good. Any other questions from audience? If not, let's thank Vino once again. So the next speaker is Jon. So please.
Okay, so what I was doing was how to prepare a Gaussian input file without going through gausview. So basically what I did was I went into gausview and I made a molecule. It was just a a 2 titanium molecule. And what I did was I saved it and I did the geometry optimization with molecular mechanics. And then that gave me a .log file. So what we want is we want to have that .log file from our molecule, and we need to change it into a text file by turning it into an XYZ. We can do that through the Babel function. And basically, the bottom part here is me just moving my file and reorganizing into a different directory. And the second thing that I did was, once I was in where I wanted to be, I copied the .xyz file as a .com file. So with the nano command that Stephanie showed us, you use your nano and then the file, or the .com file name, and what you're given is you're giving your list of atoms and their relative positions. And so the next thing we'll want to do is kind of what they had showed us is we have a header that we'll want to use to add to this file so that we are entering the correct commands to run the right calculations. So what we have is our CHK, and what you want to do is you'll want to type in the file name that you'll want it to save as a CHK. So in this case, I took the file that Dr. Killen created, and so the TI04H4 is a generic that you can change out for whatever file that you're making. The memory is how much memory you want to run. Proc shared are the number of processors that you want to use. The HF is for the Hartree-Fock, and then Vino just showed us about basis sets. The LANO was the Los Alamos National Laboratory, right, that we send it to. And then we need a blank line, and then there's an extra line for typing so you can write any comments that you need or help you remind what you're doing, another space. And then what we have is 0 and 1. 0 is the charge of the molecule, and 1 is the spin multiplicity. Those can be changed as needed for the molecules that you have. So what I did next was using this cat command, you can combine two types of files. This bin header is the file that Dr. Killen had made, and the next one is the file that I had. And so what I did was I combined them, and then I just went to the directory to show that the new combined file was now created. And so what you get is you have your new file, or if you run nano, the nano command on the new file that you just created, this will come up. And so what you'll want to do is you'll want to go in and edit that. So from the previous slide, right above the positioning of the atoms, I took out that file name and those extra numbers because you want your headers, a space, a comment line, a space, and then charge and spin multiplicity, and then the positioning of the atoms. And then you want to make sure at the end you want to hit enter a few times and leave some blank spaces below. So submitting is run Gaussian and the file name. I guess I should say in here, once you have completed editing, Control O will save it, hit enter, and then Control X will exit. You can use the run Gaussian command in your file. And to see if your file is finished or not, you can use what is, well, I have the watch command, but what you can do is just qstat, and then the vertical line grep, and then the job number. That also will bring you to watching it. And so after it is finished, you can use the more command to open it and look at all the data that you have gathered. And at the end of the file, if you see it and it says normal termination of Gaussian 09, that's good. That's what we wanted. Or you can also use a tail function. And that is how to submit it.
Okay, thank you very much, John. But thanks, the speaker. So, any questions to this important practical manual?
So yeah, while the file is running, you can actually open it, but what you will only receive the information that has been completed. So you might only have half of it, and you'll be looking for what you were looking for, and it's not there yet. So yes, you can open it, but it won't give you all the data that's been prepared by the calculations. Yeah, you can open. Because as soon as you submit it, it'll create the new files. So when you submit to run Gaussian, it will create a new .log file and the .err file. So you can open either one of those, but they'll only contain as much information as the time it was running. So it might not do you any good to have a half-finished calculation. But no, it won't change. It'll still keep running until it's done.
Any other questions? Oh, please switch on the microphone.
So in general, in your input files, there's two main context. One is for what kind of calculation, and also what kind of a method you want to use to do the calculation. And the second part is the geometry information for your molecule. Am I right?
Yes.
Okay. Any other questions? But then let's thank John once again. And the next speaker is Shelton with a story about how to read the files that has been created during the successful computation and what can be extracted from there.
Good afternoon, everybody. Yeah, in this topic, I am going to just talk about how to extract the information in a log file without using gausview. So in this case, for example, I'll use which I created the files of titanium tetrahydroxide in the lab. Here I am going to use that file and its log file. In order to trap up here, you can see that the calculation summary which I obtained by using the Gauss view. In order to extract the data in the log file, just I have to type the more command and the file name of log file name followed by the directory and enter it. Once you enter, you will get the window like this. You have to enter here. Once you enter like this, you will get step by step each and every information which are included in the log file like this. Here it is. We can extract the total energy. When you find SCF done, you can find it, the total energy. The total energy is here in atomic unit. If you want, you can convert it into electron voltage or can be converted into joule. Done. Still you didn't extract all the information included in the log file. Once you enter it, again you can get it. If you extracted all the information, you can find that word normal termination of Gaussian. Now, how can I find out the eigenvalue of the titanium tetrahydroxide? In order to obtain that, I have to use the command grep eigenvalue followed by the log file name. Once you enter it, you will get here the eigenvalue of the titanium tetrahydroxide. Yeah, by using these values, how can I find that calculating the HO value cap? So in order to do that, I have to say the band gap energy is equal LUMO energy minus HOMO energy. What is LUMO? HOMO means the highest occupied molecular orbital, and the LUMO means the lowest unoccupied molecular orbital. The energy difference between the HOMO and LUMO is termed the band gap energy. Now, how we can extract the HOMO and LUMO from this eigenvalue? The last alpha OCC dot eigenvalue, that is the HOMO value. You can extract that from this. Now, extract the LUMO value, that is first alpha virtue. The last alpha OCC means the last alpha that is occupied. Here VRT, that is virtue. From here you can take that word. By subtracting each other, you can find band gap energy of this titanium tetrahydroxide. So calculating the electron affinity of titanium tetrahydroxide, here I am going to use the Koopman's theorem for finding the electron affinity. The Koopman theorems allows the calculation of electron affinity as the energy of the lowest unoccupied molecular orbitals of the respective system. Here that LUMO is minus 0.00751. So the electron affinity of the titanium tetrahydroxide is this. The same things, in order to calculate the ionization energy, here we can't directly extract the ionization energy of the information extracted from log file, but by using or by generalizing the Koopman's theorem, we can find out the ionization energy of titanium.
Okay, thank you, Shelton. That's the next speaker. Any comments, questions? Okay, let's go then. Let's thank speaker once again and go to the next presentation. So Sheldon presented us the structure. Please go ahead. I will just introduce. So the next speaker is Qiang Wei. he will tell us the story, continuation of the previous one. So how to make an analysis and extraction of molecular orbital energy in an automatic way. Please, floor is yours.
Hello. So I'm gonna talk about the PL script to extract the density of state out of the log file. And first, we should know what the density of state is. The density of state of the system describes the number of states per interval of energy at each energy level that's available to be occupied by electrons. And the high density of states means that there are many states available for occupation. And if the DOS is 0, it means no states can be occupied. And the script we're using is the right highlight here. So it has two functions. One is that it can take the energies from the log file, and also it can create the DOS file. So in order to run this, we have to have the command kill and also the path to this file. And this log file is what I got from Dr. Keating's folder structure they already made. And
yeah, please try to mount it.
is it okay, huh?
Yeah.
And so then we can figure out the energy of the orbital energy from the log file. Here is the different number of the orbital and the energy list in here. So the number here 2, it means like 2 electrons in this orbital. 0 means no electrons. So there are actually 4 arguments in the script. Here we can see the first one is the Gaussian optile. This one doesn't really matter. So previously we got like 4 numbers in here. These 4 numbers is actually, the first one is the number of energy steps. Then the second one is the width of the Gaussian in DOS. And the last 2 numbers, one is the energy down to the HOMO, and the other is the energy up to the LOMO. So the reason why we the width parameter matters, we can see the Gaussian wave function here. The width parameter is actually the sigma, the c, which is sigma in here. And when we change it, the Gaussian curve changes shape. So like this one, the 0.2, we can see the blue line got the variance sigma squared got 0.2, and then this curve goes higher, and it goes larger. It goes the red line, and the yellow line shows the curve goes like lower the height. The variation, the variance is smaller. The curve is getting lower. Yeah, that's.
Let's thank Chen. Any questions from the audience or maybe from the youth?
Sorry?
Any questions to the speaker?
Yeah, we can hear a lot of disturbance.
Okay. So probably when speaker is speaking, we should check that all other microphones are off. Then maybe it will be more clear sound. I do have one question. So if you want to model some realistic situation, how would you choose the value for this width? What would be the deciding factor? Any ideas? Do not hesitate. This is too big. It is educational, but practically it should be smaller value. But what would you think would be reasonable? Anyone in the audience want to give a suggestion? Okay, yeah, the number is okay. It was Vinod suggested using 0.02 electron volts, right? And why? Any what? Yes, but which energy? So the idea is that in real life, all molecules at low temperature, they experience thermal motion, and the energies of each individual orbital is shaken. So it should be an error of the order of thermal quantum. You just take the energy of corresponding to room temperature, convert it into electron volts, and use it as this parameter of width. Okay? Those are just traces from previous version of the code. The 2 and 2 at the end do not change anything. Okay, more questions to the speaker? No, but thank once again. So the next presenter is Yuchi, and she will provide deeper details about possibility of analyzing energies of molecular orbitals and a possibility to visualize them.
बोलायरला तो भाषा नहीं चलिए लगाए
Can you hear me? Yes,
yeah,
yes.
yeah.
So I want to tell you how to present it.
I don't know, there's something.
Okay. Those. Can you hear me now?
Yeah, it's
Yes.
good now. Yeah.
Yes, it's good.
So I want to tell you how to present the orbital energy through the density of state. So as Qiang said, the density of state is a system to describe the number of states per interval of energy at each energy level. Then this formula is this function will the density of state also can be defined by this function. And Qiang also said how to extract the DOS. We just need to type this command, then we can get this log file. Then we want to rename to dos.log because in the next step we need the dos.log. So then then the DOS.log is contain all the density of state for the Gaussian. Then we want to how to plot the DOS. We have two methods. One, we can use Excel to open the log file. We can download the dos.log into our local computer, then open it in Excel. Then we can see like this, they have the 4 rows, the numbers. So then we want to use the first row to as x, the second as y. Get this picture. So this is our density of state picture. But we have another method to do in the SIGWIN. We can use the GNU plot the program. This is a program so we can use to get the plot the function data and the data phase, and normally this will get the better pictures. So how to use this? We just type this command, then we can run the GNU plot. Then so we want to see what's in this script. So look here, this have the four commands. So one, we just set up the line one and the type, and then we can get our output is .ps file. Then we can set up the x label is orbital energy, is first row numbers is orbital energy, and set the y label as DOS. That means the second row numbers is DOS. Then we the plot this dos.log file, and using 1 means the first row as x, and 2 means the second row as y. And that is W is width. We use the straight line to plot. Then we can get a file. But this script we can only get the .ps file, but we cannot open in our computer, so we need to convert the .ps file to PDF. We only use to type this command ps2 pdf wr, then get your .ps file names. Then we can get the same name but in PDF. So then we can download it, use your scp command. So the scp command is like this. Then we can use our computer to open the PDF. This is use the GNU plot to get the density of state picture. Then we compare these two. They get the same, but I think the GNU plot is get a better picture than Excel picture, and it's maybe more easy because I get the GNU plot density of state picture only get in type some command, but the Excel I maybe use the 5 or 10 minutes to get because I need to organize the numbers. So maybe I recommend to you use the GNU plot to get the density of state picture.
Okay, let's thank Yuchi for very interesting presentation and for advocating the GNU plot software. So, any questions from the audience about this practical steps or some ideas behind it? So, what would you do to change the axis, the label on the axis?
So we can just look here. This script will only get the ZX label here. You can type anything you want.
Okay, very good. Well, if any questions, please go ahead.
What the U and W means?
I said U is use the one, that's the first row number as X. 2 is the second row as y, and w is width. So we can change it to this line. Maybe use the circle. Then you will get the picture like get a circle to connect the line. Maybe you can use star. So that means the line shape, the shape of the line. So
Okay.
maybe like this picture is content. If you use star, so it's connected to a little star. Now you use a dot like. So that is this command mean. You can change this is into star, circle, or a number, what you want.
Okay. Any more questions to the speaker? If not, let's thank Yuchi once again. And we have another presentation by Mohammad. So he will present the opportunity to visualize how the molecular orbitals are distributed in space and which practical steps need to be done to create pictures, to view the spatial distribution of molecular orbitals.
SDSU, are you hear me?
Yeah. Yeah, can you?
Okay, so actually I will talk about the molecular orbiter, how we can draw molecular orbital, what's the way we can establish the method, and at the end we give us the suitable molecular orbiter for the molecule we have. First of all, we should then do we have the appropriate orbital. So if I look over my directory and I have this file in Hartree method, and the main important file is chk file and log file. So make sure that this you have, and then any other step is going to depend on those files. So the first of all, what's the molecular orbital? Molecular orbital, as we know, is combination between atomic orbital, either constructive or disconstructive. Also, we should know the ISO value, and in ISO surface is a surface representing all location in three-dimensional space, whereas trivariate scalar field of x, y, z assume a given ISO value VIE, where F equal V holds. It's partitioned as a three-dimensional volume into distinct regions. Location inside the ISO surface have associated value greater than or equal to the ISO value. Location outside an ISO surface have an associated value less than the ISO value. By varying the ISO value, it's possible to visualize the entire scalar field. So the practical step, where the orbitals are stored in the Gaussian output. As we stated before, it's in CHK files. Do we have this file? I opened the file previously here, and we have it. Which step lead us from this file to nice picture? So first thing, we should formatting, and then generating cube files, and then plotting cube files. Actually, this step Dr. Kellen helped me to. Previously I was struggled, and then I look over more than one molecule, and this is the three main steps we should follow in each calculation. Formatting, generating cube files. What's the formatting? We should convert file from CHK format to FCHK format. Which command form CHK we should do? What's the syntaxes of using this command? Just type, in this example, for example, just type the command and then empty space and then the same name of the file. For example, I choose this file, so you should write the empty form chk, then the name of the file. So then write formatted file ch for cho for h4 fchk. How do we know that the command went successfully? We should inspect the command. So type in ls lk head no3, and then we should see the files it's formatted and switch from chk to fchk. Then the next step, convert cube file. Use CubeGen. Gaussian actually include stand-alone utility for generating cubes from the data in a formatted checkpoint file equivalent to the previous cube keyword. The utility is named CubeGen, and it has the following syntax. So this CubeGen has memory and kind, and then the type of the file, then a cube file, then NBTS format. So this example, so if I choose this file, so type CubeGen, then O is the memory, MO equal 24 is the kind, 25 is the record. You can type in 25, 26, whatever. Then the name of the fchk file, then type in cube files mo24.cube. It's important to keep this number mo equal 24 as the same as the mo24. You should know that both of them has the same number. Also, you should take care of the empty spaces between record, like CubeGen space and then space mo. These are important spaces. Once you have the cube file, you're actually already done. Then all what you want to do is just open the file. So go to Gaussian view by opening new windows. Go open, and then choose the cube files from the open file type list. So we have actually, I generated previously mo25, mo26, whatever. Choose any one you want. This picture gonna show up, and then result surface. You should also choose the new surface, and then click in the file is just show in surface available. The nice picture at the end gonna form very nice molecular orbital. And I would say thank you.
Questions are welcome. I have one.
Go ahead.
So your picture that you described as nice picture takes takes a lot of space. It occupies area around your molecule, a lot of area. Yes. Is it something that is set up forever, or you can control? You can make it smaller or bigger while drawing.
I believe you can. If you change the number mo equal ISO value.
Same molecular orbital. Can you change the ISO value? Yes.
I think you can.
So if you take the bigger ISO value, your molecular orbital will be drawn on a bigger space or smaller space. How the amount of space covered by these three-dimensional clouds depend on the value of ISO value. If there are volunteers, they can come to the microphone and tell it to all of us. Please.
I think it should be in the like reverse way. If you take the higher ISO value, then it will look smaller, and if you take lower ISO value, then you will see this one has like 0.02. If you make it as 0.01 or like less than that, 0.002, then it will be smaller.
Yeah, very good, very good. Thank you. Any other questions?
Yes, I have a question.
Please.
Go ahead.
This figure shows the molecular orbital, and can you tell me about there is space between those orbitals? Like, if there was bond, there should have been orbitals shape, something like that, isn't it? Like, why are the figures disconnected?
Well, I think I choose it depend upon the see what I hear. Yeah, it's same depend on the kind of the orbital I choose. So if you change the kind of the orbital, O23 or whatever, it's gonna change the picture overall. So this is just exist in this kind of orbital. The shape maybe gonna change, maybe this more connected or something by just change the kind.
Okay, can I
Yeah.
add a comment? So there is a big theory of molecular orbitals that was developed even before computers were brought in. And there are concepts of bonding and anti-bonding orbitals that reflect the chemical structure of a compound. And in the simplest compounds, the orbital continuously connecting two ions corresponds to formation of chemical bond. And if there is no electron density between ions, it is in a basic case corresponds to absence of the bond. But those are limiting cases. There are a lot of exotic situations when this analysis is not as simple, cannot be processed in a simple way. And here we're not discussing the analysis, we're not using our chemical intuition to analyze this orbital. We could do it as a separate task. Here it is just a procedure how to extract any molecular orbital from the calculation. That make sense?
Okay, thank you.
Okay, let's thank Mohammad once again. I want to conclude and thank all speakers once again. So it was a great work, great effort of bringing up this manual, these procedures, and I hope that you got some insights from listening to each other. To my understanding, we do have a vacation week, and we meet next time on the March 12th. So if you do not mind, I will entertain you with a little homework in between, but I'll try to make it doable. Okay, thank you all, and see you in a week and a half.